All right, we are back. Let's solve the weekly 371. Let's do it. So let me share the link in chat and pin it. All right. So this is the weekly contest that was yesterday. There are 4 questions as usual. Get going. Maximum strong pair XOR 1. So you might see that question 4 is the second part, the second version of this problem, but let's focus on the first one first. You are given a 0-index integer array, nums, a pair of integers x and y. It's called strong pair if it satisfies the condition that the distance between x and y is less than the minimum of the two. You need to select 2 integers from nums such that they form a strong pair, and their pairwise XOR is the maximum among all strong pairs in the array. Return the maximum XOR value out of all possible strong pairs in the array nums. Alright, so this is Q1, it's an easy. So we probably can get away with a brute force approach. So yes, here the size is up to 50. So we can do a quadratic solution that goes over all the pairs, and it should be fast enough. So let's go for it. So we go over all. So yeah, one thing they say is that you can notice that you can pick the same integer twice to form the pair. So it doesn't matter, the order doesn't matter, so we don't have to consider like 2, 3, and 3, 2 in this example, because all these operations are commutative. So the XOR, the minimum, and the absolute difference. So we can start here from I to n, and now let's do this, and now we check if they satisfy the condition, which is this one right here. And if they do, we get the maximum. So we update the maximum, and this is the XOR operator in Python. And so yes, so 0 is the least value that we can get. Well, no, they are all positive. They are all positive. But yes, if you XOR one number with itself, you'll get 0. So you can get 0, and you cannot get less a negative value. So 0 is a good default value for the maximum so far variable. So we pass the examples and we get accepted. Cool. So let me share the link to my submission, and let's move on to the second one. So high access employees. you're given a 2D array of strings. So you have a pair for each element. You have a pair with the name of an employee and the access time of that employee. All the access times are within the same day. The access time is represented as 4 digits using the 24-hour time format. So we get 8 o'clock, 22:50. All right. So an employee is said to be high access if he has accessed the system 3 or more times within 1 hour period. And times with exactly 1 hour of difference are not considered part of the same 1 hour period. Okay. So it has to be less than 60 minutes. Access times at the start and end of the day are not counted within the same 1 hour period. Okay. So this does not matter, right? Because they say it's all within the same day. So this clarification I don't think makes sense. Return a list that contains the names of high access employees with any order you want. All right. So notice, the first observation here, hey, no condom Chris, how's it going? So notice here that the first observation is that every employee can be handled independently, right? Because you want to assess whether an employee is high access, and that depends only on that employee's access times. So you can first separate all the access times by employee. So let's create the groups. Let's use a dictionary, and so here we have the name and the time in access times, and we want to group by the name of the employee, and we want to add this time. But every time you get this times, so we want to check the differences between times to know whether the distance is less than 60 minutes. But here we get this format that is not easy to compare. So it's not easy to know how many minutes. So let's deal with it right now at the beginning by parsing the time. So we get the first 2 digits are the hour, and let's convert it into minutes. So we multiply every hour by 60, and then we parse the minutes, which are the last 2 digits. So this should deal with that. So let's parse them. I don't know if you did the bi-weekly, but it had cool combinatorics, 01 solutions for Q1 and Q3. Oh, that's interesting. So yes, I did a stream today. You can find it in my YouTube channel. But I didn't know that there were combinatorics solutions. So for Q2, I did a one loop and then one calculation. But so are you saying that there's a closed formula without a summation for Q1? Okay, that's interesting. So I'll think about it, and maybe I can do another stream. And with the Yeah, so that's interesting. So for Q3, so how would you do that? So maybe, so maybe you can count the complement. So for example, you can check the solutions that have 0, else, and yes, I would try to count all the combinations and then subtract the combinations that don't have leet. In any case, I'm digress. Let's finish this one. So we group them by name, and now we are going to process. So we can return them in any order, so that doesn't matter. So the name and the times in the groups, and we want to know, so we want to sort them so that we can check groups of 3 that are consecutive. So if we want to go over from number 2, because we want to consider groups of 3 consecutives, and this group starts at time I minus 2 and finishes at time I, and if this difference is less than 60, then we found a high access. So we found an interval of 3 within 1 hour. So in that case, we add the name into the result, and this should be it. And we get A, C, D. So they're in different order, but it doesn't matter. So accepted. Cool. So let me share my submission. All right, so this one, the minimum operations to maximize the last elements in arrays. So you're given integer arrays nums1 and nums2, both having length n. You're allowed to perform a series of operations, possibly none. In an operation, you select I in the range 0 to n minus 1 and swap the values. So this is the corresponding, you can swap corresponding values, so the I for both. Your task is to find the minimum number of operations required to satisfy the following conditions. So nums, so the last element of nums1 is the maximum of all of them, of all the elements in nums1, and the same for nums2. Return an integer denoting the number of operations needed to meet both conditions, or -1 if it is impossible to satisfy both conditions, and the sizes are up to 1,000. Okay, yeah, I don't know why this looks small. I think you could do this for 10 to the 5 easily. So yes, the first observation here, so this whether you get the maximum depends on the last elements. So the last elements could be as they are initially, or they can be swapped. Those are the two options. And once you can try both of them. There are only 2 options. And once you have determined the last one, then notice that all the others are forced. So if they are, so every pair of elements in the corresponding elements on each array can be swapped independently, right? So if they satisfy the condition in their initial positions, then you don't have to swap them. You can leave them as it is, and that decision does not change anything for the other. So you can make that choice independently, and if they do not satisfy the condition, then you can try swapping them, and so you pay the cost of one swap operation, but you have to check whether they satisfy the condition after they are swapped. If they don't, if any of them don't satisfy them, then you cannot do it and you're done. It's impossible. Or if they do, then you pay the cost and you keep going to all the others. So let's see how. So let's create a function cost for calculating the cost. Or mean operations. So this is the option where we do not change we don't swap the last one. But here we can swap. Let's try by swapping the last one. So this is the last one. And in Python, we swap this way. So we swap them and we retry. We retry this, but we need to be careful because we already did a swap, so we have to add 1 to whatever we get after that. And yes, and let's say, so how do we indicate that it's impossible? Well, we can return infinity. So, but here we have to translate it to -1. So if res is infinity, then we return -1, otherwise we return res. So now we can do this. So let's define for convenience, let's define n again. So we want to go over every element except the last one, and there are 3 options. So let's first try to see if they satisfy the condition, which means that this must be less than or equal to the last one and nums of 2 of I. So this is the case where we don't swap anything. So if it is, then we don't do anything. We are good. Then if we are not good, then we try to swap them. We try to swap them, which means that here instead of nums1 we use nums2, and here instead of nums2 we use nums1. And if it is true, then we're good. We keep going, but we add 1 to the result. And if none of those are good, then we have to return infinity. So we get the right answers and accepted. Cool. So yes, notice that, so I heard that some people were trying to do this by dynamic programming, but notice that the choice is the only choice that matters is this choice, the choice of the last one. Then every other choice depends on the last elements, and it's independent. So whatever you do, so you have to make the ith element satisfy the condition. You are forced to make it satisfy the condition, and that choice does not affect any other index. So that's why you can do this greedily. You don't need to do dynamic programming. Okay, so now for the last one, maximum strong pair. So okay, this is the same problem as Q1, but in this case we cannot do a quadratic solution. So let's think about it a little bit. So what this condition, first we need to understand this condition, which is not so clear. So in the brute force approach, we just copy what it said here with an if statement, and that was it. But here, so notice that the original order doesn't matter, right? Because we are pairing every element, and this does not depend on the index. It just depends on the values. So that means that maybe we can change the order to make this simpler. And if we sort them, then notice that if we are trying to, hey, thanks, the land be useful. Thanks for the follow. So notice that if we sort them, and let's consider the first element. Let's say that x is smaller. Then this turns out to be, so if we have that x is smaller than y, then so we're trying to see this, but this becomes just, so y minus x, this is going to be non-negative, and this is just x. So here the condition becomes this. So maybe we can go over. So that means that if we are considering value x, then all the values that can be paired with x are going to be in a range from x up to 2x. All those values are going to be can be paired with x. So maybe we can do a type of two pointer technique, so that we can keep track of the range that has all the candidates to be paired. So let me show you. So if we have the L value, and let's say that we have a right pointer, while r is less than n, and we satisfy the condition, which is that nums of r. So we can even nums of r is less than 2 times this. We want to increment it. So now we have this range from L to R, where we have all the candidates that can be paired with nums of L. However, so we need to find the best one, but we cannot iterate over them, because then we're again going to have a quadratic algorithm. So maybe we can add those elements into a data structure that can, given nums of L, and the data structure contains all the elements that can be paired with L, with nums of L, then it can give us the best, the maximum XOR. So how would that look? So that would look like this. So here we would add nums of R, because we are extending. So this is we are imagining that we have a data structure. So here we would add nums of, so to this structure, and here we would query the data structure, and we will try to get the maximum XOR for nums of L, and in the end we would remove nums of L, so because now L is going to be removed, and we're going to go to L plus 1, right? And so here we want to update the maximum, right? So this contains values that can be paired with nums of L. All right. So now what? Now, so this is something that I know because I've solved these problems before. So there is a data structure that has this operation, this max XOR query, and it is a data structure with bits. So we're going to create a trie that has so it's only going to have 2 children. So the next element, initially we don't have any, and it's going to have 2 because this is a bit binary trie. Every node has 2 children, 0 or 1, and then we are going to have a count, the count of how many elements are in that subtree. So we're gonna have an add element that is going to get a node of the trie, or let's call it trie, and we're gonna have the value, and let's add this so that we can implement the addition and the removal together. So this by default is 1. We want to add 1 occurrence of x, and so we add the delta to the root of the tree, and the height of the tree is going to be 20 because of this limit that we have here. So numbers are going to have up to 20 bits. So we go from most significant to least significant digit. So this is going to be B and up to 0 down. So now we want to check want to get the ith bit, which we get this way. And this is a standard code for, so if the next of B is none, then we need to add a new node there. And now well, this is not self, this is try. And so now we update the pointer to the next node depending on the current bit, and we want to update the count as well with delta. Okay, so just for convenience, we can have a remove, which is just going to add try, and the delta is going to be -1. Okay, so now we can have the try data structure, and we could have, so this is going to give us the maximum XOR of the try for value X. So now we have all the interface is completely defined. So here we're gonna create the root of the try, and here we're gonna add values to the try, and here we are going to remove them, and here we're gonna call max XOR operation with nums of L. And so now this is going to be similar to the add function, but the catch is that we know, so we're going from the most significant bit to the least significant. So in order to maximize the XOR, we want to go for we want to have a 1 in the most significant bit. If we can get a 1, this is something that always happens when you have lexicographical order. You want to get the maximum value for the most significant digit first. And when do we get a 1 in this position? Well, when we get a 1 in the XOR when the bit of the pair is greater different than the bit of X, right? So let's start coding this. So again, we go from the most significant to the least significant, and we get the bit, the ith bit of X, and now we want to try to find a number that has the opposite bit. So if B is 0, we want a 1, because XOR of 0 and 1 is 1. And if B is 1, we want a 0. So one way to write that is, so let's write it. So this is what we want, what we would prefer, let's say prefer, is this will toggle B's bit. So if we get we have 0, it's going to give us 1. So do we have the bit that we prefer? That's going to depend. If it is none, if we don't have children on that with that bit, then we won't have it. Or if we do have it, but the count, if we do have it, but the count is 0, then we're out of luck. We don't have the bit that we prefer, but we go with the other bit because we are forced to do it. So in that case, we update the try next of B, and here we go with the bit that we prefer, and we are going to set that bit to the XOR result, because like I said, we wanted to make that a 1, and we succeeded in this case, so we set the result to 1 in the ith position. So let's see, this gives the right answer for the examples, and let's see if it passes. Okay, wrong answer. Why? So what is the, so this expected 0, we got a bigger element. So is this correct? So we prefer the other bit. So in that case, we cannot get the bit that we prefer, so we go with B. Otherwise, we set the bit and we go with the one that we prefer. And here, so this is weird because this is the same solution that I had during the contest and I got accepted. So let me check if I resubmit it. So maybe, so yes, I get accepted. So this is a mystery because I think this is the same thing. Let me double check. So, okay, so here you get the max XOR. We remove the L value. Oh yes, I forgot to sort. Okay. Could happen. So yes, it was a mystery that it worked. Let's see if it works now. Yeah, I just saw your message. Thank you for noticing. Ezra flag. Cool. So now we got it. Let me share my submission. And that is all. So yes, NCC, I'm gonna think about what you told me about the closed form solution to the bi-weekly questions. So yeah, but this is all I have for this contest. So see you in the next one. Bye bye.